Yeah, welcome to demonstration of the MLT-Telos multi-level modeling language. In this episode, we shall look at the definition of MLT-Telos inside ConceptBase, and in another episode we look at the example models. So the focus here is on the theory behind MLT-Telos. We use implementation in ConceptBase to show the definition. So let's start off this simple example of MLT-Telos. This includes the example, but also all the definitions that we need. So to show them, we start the textual view. Let's make it a little bit bigger. So that's the example, but we can also go to the module where the definitions for MLT-Telos are included. The example is a submodule of MLT-Telos, which is inside the home module, and that's inside the system module, which has a basic definition of the old Telos language on which MLT-Telos is based upon. So let's check this MLT-Telos module and show the content, and then we see the definition. So MLT-Telos is joint work with these colleagues, and yeah, it starts with the definition of some predefined types. Entity stands for any object. Type stands for objects that are types, so that have instances. And individual stands for objects that don't have instances. The power type relation used in MLT-Telos is defined here. So types can be connected to other types by the power type relation. And this is declared to be irreflexive, antisymmetric, single, and reverse single, which in combination means a one-to-one association. The specializes construct between types is for subclassing, and that is reflexive. So any type is a subclass or subtype of itself. Antisymmetric and transitive. So a subclass of a subclass can be transitively followed. A subclass of the subclass is also a subclass of the original superclass. Then we have some more concepts for categorization that splits a type into subtypes. And in particular, we have disjoint and complete. And partition means it's both disjoint and complete. We'll have a look at that later. Proper specializes is like specializes, but then the two types must be different. So that is defined by this rule, which is derived from an axiom of the original MLT star language. So if T1 specializes T2 and they are different, then T1 proper specializes T2. This is the first deductive rule. So in ConceptBase, in our Telos, we write down deductive rules as an implication, and we have a conclusion predicate like this, and then we have a condition. And all variables that are in the conclusion predicate must be universally quantified here, and that happens to be just T1 and T2 in this example. Now let's look at individual. So individuals may not have instances, and that is done by a constraint. So there may not be a Y of entity that is an instance of an individual type. Sorry, an individual object. And whenever something is an individual, then it cannot be a type. So these two classes are disjoint. It's also derived from axioms of MLT star. In MLT star, a type is just an object that has at least one instance. In ConceptBase and all data log-like approaches, we have the closed world assumption, so only things that are declared explicitly are existing. So if we want to define a type in this way, then we must also declare the instance explicitly so that we know that there is an instance of this type. But that is, when you define types, that is not the best strategy. So you want to say that something is a type and later define some example instances, like when you create example models. So originally, a type has no instances in a concept-based implementation of MLT. So we cope with this problem to distinguish types from individuals and by these so-called query classes. That the first one returns those types that have directly or indirectly an individual as an instance. So directly is this case, and indirectly means you have another type T1 which fulfills this condition, and that is instance of this. So this is mimicking the transitive closure of the instantiation relation. And once we have that, we can make the complement, and that are the type that currently have no individual. So we can see which types have no individual. Next is the semantics of the specialization construct. So when T1 specializes T2, and there's an instance E of T1, then E must also be in T2. That's a rule that derives instantiation to the subtype. Sorry, to the supertype. T2 is the supertype, T1 is the subtype. So instances of the subtype are also instances of the supertype. Yeah, proposition is the most general class in ConceptBase. So anything that we declare here is also an instance of proposition. This constraint here says that when we explicitly declare something to be a specialization of something else, then they must be different. So we may not explicitly declare a cyclic specialization. That's not a very important constraint, but we have that here. This rule here is the most important rule for power type-based multi-level languages that derives specializations from power type relations. So if T1 is a power type of T2, and we have another type T3 that is in this power type T1, and this T3 is not already a subclass of T2, that's the MLT-Telos specialization, then we declare it to be a specialization of T2. This is the other way around. If the T2 is a specialization of T1, then the T2 is an instance of T3. Well, let's skip basic type and order types. Then we have root types that are at the top of the specialization hierarchy, and leaf types that are at the bottom of the specialization hierarchy. Here we have the roots and constraints for the categorization. So disjoint, complete, and partitions are declared like this. So if disjoint categorization is also a categorization, complete the same, partition is also a disjoint categorization, and it's also a complete categorization. And there are two constraints that say that the categorization must operate under the power type. So it cannot cross the levels that are declared by the power type relation. T1 and T2 are must be top level types, and the categorization happens under these T1 and T2. This rule here declares that if T1 categorizes T2, and we have an instance of T1, T3 is an instance of T1, then T3 must also specialize T2. It is a bit like the power type relation. We derive specializations. This was not mentioned in the original MLT star, but it's a consequence that we derive here. Now then we have some so-called query classes for violators of the categorization, and that is in particular for complete and disjoint categorization. So if T1 completely categorizes a type this, that is the candidate for violating the incomplete categorization, and we have an instance of this type, but it's not an instance of any of the proper subtypes, then this entity, it doesn't fall into the one of the subtypes, and then it's not a complete categorization. Analogously, for the disjoint categorization, we have one entity that falls into two different types. The type that we return here as an answer, and another type that we also return. Good, so that is the whole definition of MLT-Telos in ConceptBase. I should say, when we go back here, we should have a look at these parts, the irreflexive, antisymmetric, and transitive tensor force. That is also defined, but it's in another module, so we have to go to this module and show it. So these constraints and rules define what we mean by single valuedness, necessary. So single means at most one, and necessary at least one. We have the reverse version for that, so depending whether it applies to the source or target of an association. Then we have reflexivity, transitivity, symmetry, and so forth. they are defined also by constraints or rule. For example, antisymmetric means if x is related to y and y related to x, then they must be the same. That is antisymmetric. For example, the specializes relation is antisymmetric. That is transitivity. So if x is related to y and y to z, then x is related to z. Now this predicate means explicit relation here, so that makes the rule a bit more efficient. Rather than quadratic recursion, we have only linear recursion here. Note symmetry is when x is related to y, then y is related to x. So all of these keywords are backed up by their meaning, and they are actually implemented in ConceptBase. So let's now go back. So here we see the graphical representation. That is a derived specialization link. This black link is an explicit instantiation link. That is our power type link. That is a subclass of person. Let's see whether we Good. So that terminates this presentation, and thank you for your attention.